a finitely generated group gamma embeds in homeo of the real line if and only if it satisfies an algebraic property which is being left orderable. And left orderable means that there is a total order on the group which is invariant by multiplication on the left. So if you have f smaller than g, then h of f is smaller than h of g for every h in gamma. So I will consider the space of all left orders on gamma. I will put them inside a single space. So I will consider all left orders. This is a very natural idea, and actually has been revealed very important. It has led to the solutions of important conjectures to look at the whole space of left orders on a group. And what is nice is that, well, for the case of finitely generated group, you can define a natural metric in this space so that it becomes a metric space. Okay? You can define, say, that the distance between two orders equals, say, 1 over it depends also. The question will also depend on the normalization you will take for this. Okay, so I will take 1 over. Let me think a little bit. 1 over 2 to the n maybe, where n, where the two orders coincide on the ball of radius n minus 1, but do not coincide on the ball of radius n. So if I have two orders, at some moment they become different. So I look at the first moment where I see that difference, and I keep this number. Okay, this is a metric, and actually this space with this metric is a compact matrix space. Okay, another thing which is interesting is that there is a very nice action of gamma on this space by conjugacy. So I will come back to this later, but it's a nice action by conjugacy, but since the orders are already invariant on the left, actually this is an action on the right. But the theorem says that the space of left orders of a group cannot be infinite and countable. So it's either finite or uncountable. It contains a Cantor set. Well, there is a better way to think about a left order. Better way is to think about what is called the positive cone. The positive cone of a left order is the set of elements in the group that are larger than the identity. And what is nice with this is that gamma is the disjoint union of this positive cone, which is a semi-group, the set of negative elements, the inverses of elements in this positive cones, and the identity. Okay? And this is a semi-group. If you take two elements which are positive, H1 and H2, then if you multiply this equality on the left, you get H1, H2 is larger than H1, but H1 is larger than the identity, so you get that H1, H2 is in the positive column. Okay, group itself acts on this space of left orders. So there is a natural action. So given an element F in gamma and an order on the group, there is another order which is the action of this element on this order. Okay, and the new order, let me denote it F of this is the order whose positive con, so that the set of positive elements are the conjugates of the set of positive elements of the original order. The action of the free group on two generators in its space of left orders is transitive. Which means that it is it has dense orbits. So this is a theorem by my student, former student Cristobal Rivas, but actually it was somehow implicit in the work of Stefan McCleary from the 70s. A fixed point for this is a point for which conjugating a positive element still gives a positive element, which means that the order is a bi-order, is invariant on the left and on the right. And there are many bi-orders on the free group. So there are fixed points, but there are points for which the orbit is very, very complicated, and they cover the whole space. Well, the closure of the orbit is the whole space. Okay, this is more or less the structure. Actually, there is another closed subset which is invariant, but anyway. So the question is, can the action of the group for a certain group in the space of left orders of itself can be minimal? Gamma is left orderable and finitely generated. Suppose that, so this is a question, not a statement. Suppose that there is no free subgroup inside gamma. And the question is whether there exists a group homomorphism from gamma into Z. In case you replace this property by amenability. So this is known to hold for gamma amenable. And gamma embeds into the group of C1 diffeomorphisms. Then gamma surjects into Z. Or actually, it's better to write this way. Gamma has a non-trivial homomorphism into the reals, if you wish. Gamma finitely generated, left orderable, with a property which is very important in this context, well, in any context. It is called Kasdan's property T. Oh, there are many equivalent formulations. One of the formulations is that if every action of gamma on a Hilbert space has action, I mean isometric action, an action by isometries. So an action by isometries is an action by maps, which are compositions of rotations and translations. Okay, and the rotational part has to be a representation, unitary representation, and the translation has to be a cocycle with respect to the unitary representation. So it has a version in terms of cohomology, but I prefer this version, which is more geometric. So every isometric action of gamma on a Hilbert space has a fixed point. Okay? Embeds into the group of diffeomorphism of the circle with some regularity, say C2, and is infinite, then gamma is not T. Has no non-trivial, of course, no, this action, say, has no faithful action by C1 diffeomorphisms. Okay,